So we have Romain Dujardin telling us about the dynamical Manin-Mumford conjecture. All yours.
Thank you. So yes, you can hear me. So thanks a lot to the organizers. I don't know if Sabia is here. No. Anyway, so yeah. Sorry. So thanks a lot for the organizer for all this organizing work, very fine work, and for inviting me. Okay, so today I want to report on a recent work, very recent work with Charles, which was here, and Matteo Ruggiero in Paris, about this dynamical Manin-Mumford conjecture for plane polynomial maps, and which was released on arXiv just a few weeks ago. So it's a very recent work. So it's another talk in algebraic and arithmetic dynamics. So it is very much related to Laura's talk, and so you will. So it will be very helpful for me that she already did a lot of the preliminary work. Anyway, so even if I'm absolutely not an expert in this area, I would like to start by recalling some basic problems of arithmetic geometry which motivate all of this. So arithmetic geometry is the field of mathematics which studies rational points on algebraic varieties. So its initial motivation comes from the study of Diophantine equation, such that the Fermat equation, which is here, okay, when you want to find triples of integers satisfying this equation, actually you can translate this into a more geometric problem by considering this curve. So it is a curve in the plane defined by this equation xn plus yn equals 1, and any solution to this equation corresponds to a rational point of this curve. Okay, so and there are plenty of situations in arithmetics where you want to solve a certain Diophantine equation, and actually it's equivalent to finding rational point on the curve. So that's the basic motivation for arithmetic geometry. So more generally, you take a variety which is defined by a certain number of polynomial equations. So these equations these polynomials are defined over the field of rational numbers or maybe algebraic numbers. And maybe you see it as a subvariety of affine space. So this notation AK is for the affine space. And it's important not to say that it is Q to the power K or Q bar to the power K, because the field will change. So it's the affine space over some field, and choosing the field properly will be part of the work. Okay, so you take this subvariety defined by a number of algebraic equations, and you want to know what is the cardinality or what is the structure of the set of points, rational points in this variety, and more generally of the set of points in this variety whose coordinates are in a given number field, like we don't know, quadratic integers or whatever you like. Okay, so the most famous theorem in this area is certainly this Falting's theorem, which says that if you take a plane curve, so a curve defined by one equation in 2 dimensions, and if you assume that if you view this curve as a Riemann surface, okay, and if as a Riemann surface it is smooth and its topological genus is bigger than 2, then, so if you projectivize, you make it compact by projectivizing, then in any number field, this curve has only finitely many points. Okay, so a corollary of this theorem, which is now obsolete because the full Fermat last theorem has been proven later, is that for every degree bigger than 3, so this condition 3 here comes with this genus assumption. So the curve in this case, if you want to apply it to Fermat last theorem, the curve is exactly this one, and this is a smooth curve, and for n bigger than 2, the genus is bigger than 2, is at least 2. Okay, and so the corollary of this Falting theorem is that there are at most finitely many exceptions to Fermat's last theorem in every degree. So now it's obsolete, but I think that back in '83 that was a big thing. Okay, so I just want to make a small remark. I already made this comment. So there is something that we did here. We started with a purely algebraic problem about integers. Okay, and so now we defined a certain equation, and now we view this equation as an equation over the complex numbers, and then we use the complex numbers. So it is, of course, there's nothing extraordinary here. It's something that we do somehow unconsciously all the time. But in this talk, it will be useful from time to time to be conscious about this movement. Okay, you start with some algebraic problem, then you embed it into some bigger field, and then you use the properties of that field. So here you use the complex numbers to solve the problem. Okay, again, it's something which is very common, but it's useful to keep this in mind for later. Okay, so that's the first theorem. So here we were looking at rational points in algebraic varieties. So there is another notion of being a point of low complexity. So a rational point is a point of low complexity in the field of algebraic numbers. Right? Another way of being a low complexity is this notion of points of small height. Okay, so height is a certain complexity for algebraic numbers. So if you start with a rational number, the height is just the log of the max of numerator and denominator. So it's the number of bits you need to store it in a computer, right? And for an algebraic number, you also have a notion of height, which measures the size of the coefficients of the minimal polynomial of this point of this number x, and normalized by the degree. Okay, and so you will have I will state, I think, the precise definition of height later. So a point of height 0 is a root of unity. It's a consequence of the definition. Okay, so now we can have an analog of the previous problem. If you take a curve in C2, algebraic curve in C2, you may ask, is it possible for this curve to have infinitely many points whose both coordinates are roots of unity? So it was a problem in the 60s, which was in the 60s. It was solved in the 60s. So there is this Iara-Sertate theorem, which is actually stated in a paper of Lang. So I think we should credit Lang also on this. It's amusing that in another talk, there was a mention of a paper of Lang in 65. So I think it's a very productive year for him. Anyway, so this Iara-Sertate theorem says, it gives a complete classification of the set of algebraic curves in the plane, which contains infinitely many points whose coordinates are roots of unity. And these curves are exactly of this form. They should have an equation like this, with C a root of unity. And of course, conversely, if you look at this equation and you put X a root of unity, it's clear that Y will also be a root of unity. So it's clear that these curves do contain many points with coordinates roots of unity. And the theorem is that the converse is true. Okay, one remark here is that there's a group structure involved. Okay, so actually these roots of unity, there are torsion points in the group C star, the C star times C star. Okay, so there's this group structure which is involved and which will appear in the next slide. Okay, and so you can formulate it like this. So we have these torsion points in this group. And the statement is that if a curve contains infinitely many torsion points, then it is itself not a torsion subvariety, but a translate of a torsion subvariety by some torsion point here. Okay, so there are many variations on this statement. So it's a very important problem. You have many ways of generalizing it. And in particular, there is a way of unifying these two previous statements. No, not exactly, but at least philosophically. And this way requires just a little bit of algebraic geometry. So when you take any algebraic curve, there is the so-called Abel mapping, which maps it into a certain abelian variety. So you can always embed a curve of genus bigger than at least one into a certain complex torus, into a certain torus, algebraic torus, by this Abel map, which is a transcendental theory, okay, which is integration over path in the curve. Actually, this Abel map can be defined algebraically. So it respects the arithmetic structure of the curve, if this curve is defined over rational numbers. So the notion of algebraic point makes sense on both sides, and they are the same, they correspond. And so now you can ask this question. You take any countable subgroup of this abelian variety, and you can ask whether this image of C by the Abel mapping has infinitely many intersection points with this subgroup, which is countable subgroup. So if you take the subgroup of points over a given number field, it is actually a subgroup of the torus, which is finitely generated. So the answer is exactly the Falting theorem. Okay, but you can take other subgroups. Another one is the subgroup of torsion points. And then you get something which is not exactly the previous theorem, but which is very analogous to it, which is the initial Manin-Mumford conjecture, which was solved by Reynaud, as Laura told us. So the only possibility for this curve to have infinitely many torsion points is that it is a translate of a subgroup by some torsion point. Okay, so that was for the arithmetic geometry. So very fortunately for us, there is a way of rephrasing this problem into a dynamical setting. And that was observed as I think in this paper by Northcott in 1950. It's clearly, the paper by Northcott is clearly about this. Okay, so Laura already said this. So on this torus, you have a natural endomorphism, a family of endomorphisms, just given by multiplication by D. For any, you choose any D, like D equals 2. You have this endomorphism given by multiplication by D, and that's a very simple exercise that a torsion point is, so the set of torsion points is exactly the set of preperiodic points for this endomorphism, whatever D is. Okay, so now you can reformulate the previous statement, for instance, this in terms of dynamics. It says that if a curve contains infinitely many preperiodic points, then the curve must be itself preperiodic. So of course, when you see it like this, you want to generalize to all algebraic dynamical systems. So you can ask this dynamical Manin-Mumford question. So at this stage is just a question. Take any algebraic dynamical system, okay? Take any subvariety, and loosely stated, it will be under which conditions a curve which contains a subvariety which contains a Zariski-dense subset of preperiodic points must be itself preperiodic. Okay, and if you don't like the Zariski topology, just think that this subvariety is just a curve, and then Zariski-dense just means infinitely many. Okay, so maybe I will spend not too much time. Okay, I have some time to. So that was a very loose question, and so many hard to make it precise. So among these people, there's Laura here, but before that, there was Shu Zhang. His name is not here anyway. It will happen later. So making this precise, so a good setting to work on this problem is the so-called setting of polarized dynamical systems. So maybe it will not be useful for this talk to understand this definition. So maybe just forget it. So a polarized dynamical system is basically either a holomorphic map on projective space or a holomorphic map. So you take a certain, let's say, holomorphic or regular, if you are more algebraic geometer. You take a certain dynamical system on projective space, which is regular everywhere, with a certain invariant subvariety, okay? And then you have an induced dynamical system on this invariant subvariety. This is polarized by definition, and it is actually the set of all polarized dynamical systems, okay? And in particular, being polarized is invariant under taking restrictions to periodic subvarieties. So if you have a polarized dynamical system, you restrict to some invariant subvariety, then it is still polarized. Okay, so this observation, this last observation, says that if okay, sorry, I'm going too fast here. So there's a theorem. Okay, there's a theorem by which comes from the Briand-Duval theorem on PK, but it was generalized to several settings, in particular to an algebraic setting. So it works for subvarieties. That if you take any polarized dynamical system, then the set of preperiodic points is Zariski-dense. Okay, so in one dimension, it says that the set of periodic points for an endomorphism of P1 is infinite. Okay, which was known way before. And as I said, being polarized is stable under taking restrictions. So if you have a preperiodic subvariety under a polarized dynamical system, then in this preperiodic subvariety, you do have a preperiodic Zariski-dense subset of preperiodic points. Okay, so now, so forget about the first part of the slide. You can formulate this dynamical Manin-Mumford conjecture, which says that if you take a polarized dynamical system and a subvariety, then if now you have many preperiodic points on the subvariety, then, okay, you could be tempted to conjecture that the subvariety is periodic, but obviously no, not obviously, sorry. But unfortunately, there are counterexamples to these statements. So you need to, there are a certain number of exceptions to this general conjecture. So let me formulate it like this. If you have polarized dynamical system and a subvariety which contains a Zariski-dense set of preperiodic points, then either the subvariety is preperiodic or something special happens. Okay, so there have been several attempts to say what this special means. So I'm not completely sure this is completely stabilized now. But so there are exceptions. If you remove this, there are exceptions. But all these exceptions are maps which have a too big centralizer. So they're exceptional maps or exceptional situations. Okay, so the philosophy of the dynamical Manin-Mumford conjecture is this: unless something special happens, a subvariety containing too many preperiodic points should be preperiodic. That's the conjecture. Oh, where is it? Sorry. Okay, so I should put the name of Shu Wuzhang somewhere. Oh, yeah. It was loose, but it was also the precise version later. Okay. Okay, so now I will come to the setting of the talk. So if you got lost in all this algebraic geometry, it's time to come back. Okay, so the setting of the talk is a very special case of all this, is a set of polynomial maps of the plane, the two-dimensional plane. So again, right now I do not specify the field, but of course, many people here are complex dynamicists, so you should think that it is just C square. But again, you have to pay attention to. So, okay, let me take any field of characteristic 0 and define a polynomial map. So it is a map from K2 to K2, which is defined by two polynomials of two variables, and D will be the degree. So it is the maximum of the degree of these two maps. Okay, so there is an important class of mappings, which is, so when you, anytime you have a polynomial map of C2, you can extend it to a rational map of the projective plane. Okay, but rational, beware that in higher dimension, rational is not exactly the same meaning as in one dimension. Rational means not defined everywhere. Okay, so a rational map can have indeterminacy points. And here we will only consider those mappings whose extension to the projective plane are defined, well defined everywhere, so-called regular mappings. If you want to think in terms of complex dynamics, regular means holomorphic. Okay, so I'm considering only those polynomial mappings of the plane who have, which have holomorphic extension to the projective plane. So there is a very easy criterion for this. If you want to check this holomorphic extension, actually you just have to look at, so you look at your polynomials here and you just look at the terms of highest degree. Okay, so terms of degree D, which I denote by PD, so homogeneous terms of degree D. And a map extends holomorphically to P2 if these two components of higher degree do not have any common factor. Okay, so if you, if you take an example, it's if you can solve algebraic equations, it's very easy to check this condition here. Okay, so if this condition is satisfied, then PDQD defines a certain rational map of P1, well-defined rational map of P1. And what is this P1? This P1 is exactly the line at infinity. Okay, so you have this map on C2, you add a line at infinity to C2, and if in the terms of highest degree define a well-defined rational map on okay, I'm saying it in the wrong direction, sorry. You have this line at infinity. If the map extends holomorphically to infinity, then you will have a well-defined rational map at infinity, and this rational map is given by this formula here, which is you look at the terms of highest degree. Okay. And again, as I said, regular means just holomorphic if you work over the complex number. Okay, so that's the setting. So now in this setting, it turns out that there should not be any special examples. So this dynamical Manin-Mumford conjecture takes a very special form, very simple form. And the form is this: if you take any algebraic curve in the plane, then if this curve contains infinitely many preperiodic points, then it should be itself preperiodic. So we should not expect, so of course I did not state the definition of what special means, but you can check that the situation which is referred to as special in the conjecture does not happen for polynomial mappings of the plane. Okay, so here the conjecture is that simple. Okay, so this is what we want to study. We want to study this problem, and so it is known in a small number of cases. So one case is the case of maps of this form, XD, YD, and this is exactly this Ihara-Serre-Tate theorem I mentioned before. Okay, so these preperiodic points for this mapping are exactly the points whose coordinates are roots of unity. So I'm asking for a classification of curves which contains many points with coordinates roots of unity. So that's known. Okay, that's the Ihara-Serre-Tate theorem. And also there's a more recent theorem by, so actually it started in Gyoka, Tucker, Zhang, and then the final version was given by Gyoka and Nguyen and Ye. And it concerns product maps. So maps of the form which coordinates in independent coordinates. So P of X, Q of Y. Okay, so as you see, these maps somehow their dynamics reduced to well, it's a product dynamics of two mappings in dimension 1. Okay, and in this case, also the conjecture is known over the complex numbers, and also there will be a theorem later in a couple of slides. Okay, so before going to our theorem, I would like to say a few words about the proof of this theorem here. Okay, and explain how do you deal with such a thing. Okay, so let me explain the proof of this product case, the idea of the proof. So, and for simplicity, so as I said, the proof is true when f is defined over any field of algebraic zero, in particular for the field of complex numbers. But here, I will assume that the f is defined over the rational numbers. Okay, so that will simplify the proof. It simplifies the proof. So you start with a curve which contains infinitely many preperiodic points. Okay, any of these preperiodic points. So it is a preperiodic point under a map which is defined over Q. So its coordinates are algebraic numbers. Okay, so this curve contains infinitely many algebraic points with coordinates whose coordinates are algebraic numbers. Exercise, I leave it to you. Then the curve should be itself defined. So its equation, it is defined by a certain equation. This equation has coefficients in the field of algebraic numbers. Okay, it's not very difficult. It's actually, surprisingly, it's a linear algebra exercise. Okay. So the curve itself is defined over the algebraic numbers. And again, for simplicity, let me assume that the curve is defined over Q. Okay, there are no algebraic numbers, only rational numbers involved. And as I said, so here in this theorem, we will embed everything in the complex numbers. So we will view all these equations are equations over the complex numbers. We could have made another choice. Okay, there are other fields containing the field of rational numbers, many ones. Okay, so we work over C. And then, so we want to prove this theorem. We have this curve, which contains infinitely many points, say infinitely many periodic points, for instance. But of course, the difficulty is that this periodic, I don't claim that the whole orbit is contained in the curve, of course. Only one periodic point in the orbit is contained in the curve, and then it goes out. So you want to study this problem with ideas coming from dynamical systems. So you start, you have a curve, you have a point in the curve, and of course you want to iterate, but you're stuck because the curve is not invariant. When you iterate, you go out, and you don't know, well, a priori, you don't know what to do with it. Dynamically speaking, it's not a well-posed problem. And so there is a very important idea here, which is that you actually have an internal dynamics on the curve, okay? So you have the dynamics of the Galois group. So the thing is that this curve is defined over Q. So if you take any point in the curve with algebraic coordinates, if you look at its Galois conjugates, they will satisfy the same equation. So if the curve satisfies Pxy equals 0, you let the Galois group act on it. It still satisfies Pxy equals 0 for the same P. Okay, so the Galois group acts internally on the curve. And so somehow it gives a kind of dynamics inside the curve. So it reminds a little bit of, so there was this in Aaron's talk yesterday, there was this U invariance. You get extra invariance from a certain situation. And this is exactly what happens here. So you get this, so you have your preperiodic points, and you have the Galois group acting on it. And it turns out that the orbits of this Galois group are large. Okay, so when you start with one of these periodic points, the Galois group has many, so they have many conjugates in the curve. That's the idea. So actually they have many in different sense. So let me consider first the case of a one-dimensional map. So you take a point which is preperiodic under a polynomial in the plane and look at its Galois conjugates. What I say that if you take an infinite sequence of such preperiodic points and you look at the Galois orbit, they will eventually accumulate the whole Julia set. So the Galois orbits are large. That's a very important idea. And actually, they don't. So they're topologically they're large, but also what is even more important is that they equidistribute when you make n go to infinity. So when you take any sequence of preperiodic points for a polynomial in one dimension, and you take, so for each of these periodic points or preperiodic points, you take the Galois orbit, okay, which is something different from the orbit of the point. You take the Galois orbit, and then you put point mass at each point of this orbit, and you normalize. This is what I denote by delta mass at the Galois orbit of xn. This sequence of measures converge to the maximal entropy measure of the polynomial. Okay, so this is a part of a very big chapter of arithmetic geometry, which is called arithmetic equidistribution. So it started in this paper by Spiro, Ulmo, and Zhang, and then it was generalized to many settings by many people. So it's a very important ingredient here. But I think maybe for the moment you can just think about it topologically. So Galois orbits are large. Okay, so now how do you prove this? So remind the theorem. You want to prove the conjecture for product mappings. Okay, so now, so I assume that my curve is neither vertical nor, so for vertical or horizontal lines, it's obvious. Okay, it will contain infinitely many preperiodic points only if the curve is preperiodic itself. So now assume it's not vertical or horizontal, so it looks like this. Okay, and now you take a point in the curve. Assume it's in the Julia set. You don't need to assume this, but it's not so important. So I know that there's a place in the curve where the curve is locally the graph, and this graph intersects. The image, the projection of this graph intersects the Julia set in the base in P. Okay, so you know that somewhere there's a small graph over the Julia set. Now look, so you have many points in this curve. So I zoom here. You have many points in the curve, many preperiodic points in this curve. When you project down here, you have preperiodic points of P, and when you project down here, you have periodic points for Q. Okay. Now you know that again the Galois orbits are large. So when you project here, you will see the whole Julia set. And when you project here, you will see the whole Julia set of Q. So it means that the Julia set of P and the Julia set of Q are related by this holomorphic graph. And then you know that something special happens. This is not supposed to happen unless P and Q are very special. Okay, so this is the key. So actually what you can push this analysis further, and you can go all the way to the fact that this curve C must be preperiodic. Of course, it might be that P equals Q. So it's not so special to relate the Julia set of P and the Julia set of P, but you have actually more information than that. And so you can push this analysis up to the place where you know that C is periodic. One important ingredient is the rigidity theorem in one-dimensional dynamics, which is this Levin theorem, which says that the Julia set has only finitely many local symmetries. Okay, so you need some rigidity result for holomorphic dynamics. Okay, an amusing thing is that this rigidity result. So I'm saying that a Julia set in one dimension has few symmetries. Okay, it is not true when the Julia set is a circle or when it is a segment. So this method does not cover this Ihara-Certate theorem. So for these exceptional examples of Chebyshev mappings or monomial mappings, you actually need the Ihara-Certate theorem, which is based on the same idea, but of course, it's more special because you work with a monomial map, so you have more ingredients. Everything is more explicit. But it is also based on the idea of letting the Galois group act and that the orbits are large. Okay. So far, so good. Yes, it does. Yeah. Actually, this is what you okay. The theorem of Gioca and Guénier is not for polynomials, it's for rational maps. And then for rational maps, symmetries of the Julia set are not enough. You really need the maximal entropy measure. Okay, so yes, I should have said it before. So this theorem is true for rational maps, but then it's not a map on P2, it's a map on P1 cross P1. But it's the same idea. But then you really need the maximal entropy measure and the Levin theorem. Okay, so that's our theorem. So I come to a result. So our theorem with Matthias, with Charles and Matteo. sorry. So take any field of characteristics. So okay, one last remark. In the previous theorem, we did not leave the complex numbers. Okay, so here we will have to leave the complex numbers. Okay, take any field of characteristic 0 and take a regular polynomial map. So a polynomial of the plane which extends regularly to infinity of degree bigger than 2. Take an algebraic curve which contains infinitely many preperiodic points. So we would like to conclude that it's preperiodic, but unfortunately we have an assumption. We need to make an assumption here. And the assumption is about the curve, the points of the curve which are located at infinity. So we have an algebraic curve in the plane. Okay, so it has finitely many points at infinity. And we make this additional assumption that when you look at these finitely many points, none of these points will eventually fall on a super attracting periodic point. Okay, so it's a kind of strange assumption, but that's an assumption. Then if this does not happen, then it's preperiodic. So in particular, if there is no super attracting point at all at infinity, then it's preperiodic. Okay. So small comments, so same kind of comments I already made earlier. So the statement is purely algebraic. So in this statement, everything is if your field is just the rational numbers, everything it's about equations about the rational numbers. But we will use analytic methods. So we will use the complex plane and also the p-adic numbers, and also we will need arithmetic ideas. So there are some arithmetic in the proof. There was already arithmetic ideas in the proof of the previous one, because this well, you see these Galois conjugates and these algebraic equations. They play certainly this is arithmetic geometry. Okay, so I do have some time, I think. So I try to explain the proof, which is actually not so long. So it was a surprise to us that the proof is not so long and not so complicated. Okay, so the basic ingredient you need for the proof is the dynamical green function. So dynamical green function is defined like this. Take any point in C2. So here, think you are working in C2. So well, you view F as a map of C2. So take a point and look at its iterates, and they may tend to infinity or not. And you make this, you look at the log of the norm of the nth iterate, log plus, you divide by d to the power n. So this sequence converges to a function on a continuous function in C2, which is the so-called dynamical green function, whose Laplacian is the green current you heard of a few minutes ago. And so this function has nice properties. So here we go. It's a continuous and pluri-subharmonic function. So pluri-subharmonic means that it is subharmonic when every time you restrict it to some curve, analytic curve. And it satisfies this invariance relation: G composed with F is D times G. So sorry, there's a little clash in notation here. So the field, of course, this K here is not the field, it's the field Julia set. Okay, so just it will appear only here. Okay, so the set of points with bounded orbits, which you would like to call the field Julia set, but it's not, is exactly the set of points where G vanishes. Okay, it's clear that it's clear that if G vanishes, if an orbit is bounded and G equals 0, and also you have the converse. If a point has an unbounded orbit, then it should go very fast to infinity, and so fast that G is positive. Okay, and this locus, this K locus, is a compact subset. There's a picture just after. Is a compact subset of the plane. Okay, another important fact is that the Laplacian, the DDC of this function G, detects Julia behavior. So the support of the Laplacian is exactly the Julia set. So the set of points with iterates are locally not normal. And even more than that, it also detects the Julia behavior when you restrict to a curve. So if you take any holomorphic disk in C2, you look at the green function, it's a subharmonic function in this disk, and I say that if this function is harmonic, then the dynamics along this disk is normal in P2. So it can go to infinity, but by being equicontinuous. Okay, so that's a theorem by Ueda and Fornes-Sibony, which will be very important for us. Okay, the structure, the Julia set has a nice geometric structure, which was studied by Bedford and Johnson a long time ago. And it looks like this. So you have the field Julia set. Well, you have set K, which is not the field Julia set, because, okay, the Julia set is unbounded in C2, but the set K is compact. So there are other things in the Julia set than just the boundary of K. So in the Julia set, you have the boundary of K. It is certainly part of the Julia set, but also you have a foliated part, which is in the basin of infinity. So the line at infinity, so P is defined by equations of degree D. So when x, y is large, the image is even larger. Okay, it's like xy to the power d. So the line at infinity is an attracting set. It's even a super attracting set. And inside this line at infinity, you have the Julia set of the induced rational map. So this Julia set, it is a saddle set in P2. So it is repelling, mostly it is repelling along the line at infinity and attracting transverse to the line at infinity. So being a saddle set, it has a bunch of stable manifolds. Okay, and so these are these green curves which are drawn here. And what Bedford and Johnson proved is that the Julia set is basically the closure of the union of these green submanifolds plus the boundary of the set K. So that's the shape of the Julia set. And notice that so along one of these green curves, the dynamics is of Fatou type. So when this curve, you are Julia transverse to the curve and Fatu inside the curve. So the green function is harmonic along the green curves. Okay. So that was the first tool, and we also need the same tool now over non-Archimedean fields. So now, if you consider another completion of Q and you embed it in the p-adic complex numbers, you can do the same. You can repeat the same story. So you can define the p-adic green function with the same formula, except, well, the norm is defined like this. So you look at the max of the p-adic. What is D? D is the degree of the map. So D is a reserved letter for degree all the time. Okay, so you have this p-adic norm here of a point in CP square, and you look at the same formula. It's a well-defined the limit is a well-defined continuous function which satisfies the same invariance. Okay, so of course you don't have this picture is really a complex picture. You don't have such a nice. It's not really clear what DDC of G means. Well, even some people know how to define DDC. But okay, anyway. So for every p-adic completion of your field, you have a green function, and actually you can sum all these objects. So you take a point with algebraic coordinates, you fix a certain number field which contains the point, and then you can sum over all possible embeddings of this number field, yes, in CP for all p. So for prime numbers and also for the infinite place. Okay, and then if you sum all these numbers, you get something which is HF, which is the so-called dynamical height. Okay, which will play an important role even if you won't see it. But yes. And maybe just one comment why you want to call this a height. Well, you just have to look at the definition of the usual one. So this is downstairs is the definition of the usual height, which I defined at the beginning of the talk. And you see it's very similar, except that you just have to replace this by the green function. And actually, the green function is just equal to this, except for finitely many places. Okay, so it really looks like a height, and it is a height. Well, I won't say more about this, but so there's a whole theory of what heights can do for you. Okay, so and we will use basically this as a black box, and in particular we will use a theorem by Xu Zhang as a black box in the theorem. Okay, so that are the two main ingredients, and now we can start the proof. Great, I think. Okay, I will. Anyway, so the proof is in two steps. The proof is it's quite classical in this area. You first start with number fields, and then you extend to the complex numbers. So in the first stage, I will assume that everything is defined over a number field. So everything F is defined over a number field. Okay, you can assume that it's just the rational numbers. So you assume that F is a number field, and so we will apply, so not exactly, but let me state it like this, we will apply the same idea of Galois invariance of the curve. So you have this curve, which contains infinitely many points, and so it is essentially invariant under the Galois group. So maybe if the curve is not defined over Q, you have to saturate first it by a finite thing, and then you have this invariance. Anyway, and so you have the same equidistribution phenomenon. So if you look at your periodic points inside the curve, look at the Galois orbits, they equidistribute to something, okay? So it's a theorem by these people, Jean, Tuillier, Chamberlois, etc. And what is this something? This something is the Laplacian of the green function restricted to the curve. Okay, actually, yeah, that's the formula. Okay, and this is true over the complex numbers, but this is also true over the p-adic numbers. In this case, you need to make good sense of what this Laplacian is and what this measures, what this convergence of measure means. And so for this, you need some input of Berkovich theory. Okay, so this, if the place V is not the infinite place, then this makes sense in the Berkovich space. But again, you can use this as a black box. There is no Berkovich theory in the paper. Just, well, there is, but it is used in background only. You don't have to prove new Berkovich theorems. Anyway, another important information. So actually, we don't really use equidistribution, but it's useful for pedagogical reasons to state it like this. Another important consequence of this height machinery, which is a part of this Zhang theorem, is that actually all the points are infinity. All the points at infinity of your curve are points of dynamical height 0 with respect to the dynamics at infinity. So in particular, they have, okay, I should have stated it before. This dynamical height characterizes preperiodic points. So exactly as height characterizes roots of unity, dynamical height characterizes preperiodic points. A point has dynamical height 0 if and only if it is preperiodic. Okay, so there is a formula in this paper by Zhang for the height of a curve. And so in our situation, the height of a curve, the dynamical height of the curve is 0. So it implies that the height of the points at infinity is 0 as well. So these points at infinity, they are preperiodic for the dynamics at infinity. That is this part of this black box from height theory that we use. Okay, so let me repeat. If you work over the algebraic numbers, you know that all the points at infinity are preperiodic, and also that these infinitely many periodic points on your curve, they equidistribute after letting this Galois group act. They equidistribute to the Laplacian of the green function restricted to the curve. Okay, so now comes the obvious corollary. All these points, they are contained in this K, in this field Julia set. Field Julia set between quotation marks. Okay, so they are in a bounded subset of C2. And it's the same over the p-adic number. So they live in a certain bounded subset. So none of these points is close to the line at infinity. And the Galois orbit is the same because they also are preperiodic points. So what this second point says, which is actually the only information that we use, is that the green function restricted to the curve is harmonic in the neighborhood of the line at infinity. Just because all the periodic points live in a bounded subset. And we have this equidistribution here. Okay, so now you know you have this curve which goes through the line at infinity, and we know that it goes through a certain. So take a point at infinity, it is preperiodic, and then you iterate f, and you replace by iteration f and c. You can always assume that it's a fixed point. Okay, and let lambda mean the multiplier of this fixed point viewed as a periodic point on the line at infinity. So let me repeat: you have this curve, you fix a point at infinity. You replace by some iterate so that it is fixed, okay, and it has a multiplier. Our assumption is that the multiplier is not 0. That's exactly the assumption we made. It's not a super attracting point. Okay, so now just a bit of algebraic number theory. So if you take any algebraic number, lambda here, so that will be the multiplier, you have two important facts. So first, there is this so-called product formula, which says that if you take all p-adic norms of lambda for all possible embeddings of, so this lambda lives in certain number field that you fix, so it lives in some k prime. You take all possible embeddings of k prime in CP, and you take the product of all the norms that you see, and the answer is 1. That's the so-called product formula. That's fact 1. And second fact, there is this classical Kronecker lemma, which says that if all the terms in this product are equal to 1, then lambda is a root of unity. So it's basically the same result that the fact that points of height 0 are points of unity, are root of unity. So now if you look at these two facts, so remember lambda is the multiplier of my fixed point, then not all these terms can be smaller than 1 if lambda is non-zero. So for one of the v's, so either everything is, sorry, let me repeat. One possibility is that all these norms are equal to 1. In this case, lambda must be a root of unity. The other possibility is some are bigger than 1 and some are smaller than 1. Okay, and so in particular, there is one v where lambda is bigger than 1. So the point becomes repelling when you view it over the right place v. Okay, and so we will work with this place. So the proof now splits into two cases. First case, it is the analysis over the complex numbers. So either lambda is a root of unity. In this case, we work over the complex numbers, or the point is repelling over the complex numbers, and then again, we work over the complex numbers. So that's the local picture. So first case, assume that the point is repelling over or parabolic over the complex numbers. And then the picture is like this. You have the curve C, which goes through P. Maybe it's a singular point, so I drawn it as a singular curve just to remind that it could be singular. Okay, and this point P is a repelling or a parabolic point for the dynamics at infinity. So in particular, it has a stable manifold. It has a strong stable manifold, like this. And now this strong stable manifold so this point is in the Julia set. It's a repelling or parabolic point. So it is accumulated by plenty of other repelling points. Each of them have a stable manifold. You can select this periodic point so that the stable manifold is of uniform size. So the picture is like this. Okay, you have this orange curve, which is the stable manifold of your point at infinity, which is accumulated by other stable manifolds of other repelling points of the dynamics at infinity. Okay, that's the Bedford-Johnson picture. And now you have a contradiction, because the curve C it does intersect the orange curve, so it must also intersect the green curves. Okay, but these intersections are not on the line at infinity, because C locally at infinity it only intersects at P. So you do have intersections here. So these intersections do exist. But now at such intersection, by the inclination lemma, the dynamics on the green point here is the Julia dynamics along the curve C. But we just said it was impossible by the green, because the green function is harmonic there. So this is a contradiction. So the only possibility is that the curve C coincides with the stable manifold. And that's the end of the proof for this complex case. Okay? Now, in the periodic case, the proof is basically the same, except that we don't have such a nice picture here. Okay, we don't have laminations, we don't have this. Yeah. I think it's repelling. I think everything is uniformly hyperbolic. Okay? So if it is uniformly hyperbolic, you have all this uniform structure, uniform size of a stable manifold, and you have a small piece of lamination like this. And I'm just saying that if it's not uniformly hyperbolic, it's the same. Okay, because you have sufficiently many repelling points accumulating P. And even if it's parabolic, it's also the same. That's what the picture says. You do have a kind of a small horseshoe like that, which contains both the stable manifold of P and also plenty of other stable manifolds. And now I say that every such intersection, the green function cannot be harmonic. Okay. And now over the periodic numbers, it's basically the same picture, except that you don't have the green lamination. It's not clear, the structure, geometric structure. So you have this, but you would like to find an analog of these green curves here. Well, they do exist, but I mean, I don't know what the lamination structure means in this case. Anyway, you can imitate the argument. So you can imitate this argument, and we don't have the Furness-Sibony theorem that the green function detects Fatou behavior. Okay, so we need to do something slightly different, but we imitate this argument, and the argument is an elementary renormalization result. You work in local coordinates here, and you have that. So F is my map viewed in coordinates where Z is the coordinate along the line at infinity, and W is the coordinate along the stable manifold. And this is saddle point theory says that something like this happens. So U is the lambda. U is lambda is the unstable multiplier. Okay, so basic saddle point theory says that when you iterate a point of the form Z over lambda to the n W, you go to Z0. So you take a point which is very, very close here, and then under iteration, it goes to the line at infinity. And now you use the invariance of the green function. So you can apply. So you can use the green function. Of course, it's not exactly G because you are working near the line at infinity, and the green function is for C2. But anyway, you don't care about this. So you apply the green function to this equation, okay? And we know that the green function is harmonic along C. So when you go to the limit, the G of Z0 will be a harmonic function. Okay, but now so G of Z0 is the green function restricted to the line at infinity, or at least a version of it restricted to the line at infinity. And this point Z, this point P, sorry, which is the origin of coordinate, is a repelling point. And it is known from non-Archimedean dynamics that the green function cannot be harmonic near a repelling point in a one-dimensional non-Archimedean Julia set. Okay, so again, you get the same contradiction. Okay, so we are done with the case where the field is algebraic. Okay, so now let's go to the complex numbers. And so we use an argument which is very classical in this area of research, but still requires some care. Okay, so so-called the specialization argument. I will tell you in a moment what it means. So for simplicity, let me assume that so you look at the equations defining F and assume there's only one transcendental number appearing. Okay, so everything is defined over the rational numbers plus pi. Okay, so your field of definition is something like, so it's defined over Q bar of alpha, where alpha is a single transcendental number. So what is this field Q bar of alpha? Well, it's exactly the field of rational functions. So working over Q bar of pi is exactly the same as working over Q bar of some indeterminate. So actually, you can view this map defined over Q bar of pi as a one-parameter family of mappings. Okay, so this F can be understood as a one-parameter family of polynomial maps defined over Q bar now. And the idea of a specialization argument is always basically the same idea. So now you have a one-parameter family of mappings, and now you can pick as many algebraic parameters that you like. You can specialize, at the meaning of specialization. You can choose T to be an algebraic number. So you have an equation with pi's inside, and you replace pi by square root of 2, and square root of 3 and 4. No, 4 is okay. 5. So you have many. Well, square root of 4 is also okay, but anyway. So you replace this T by many algebraic numbers, and then you apply the first part, and you imagine that it will work. Okay, so this is what we've been doing. So again, when you fix T naught to be algebraic, then you can apply this arithmetic method. So it looks like magical, but it works. Okay. So so assume that C is a curve containing infinitely many periodic points defined over. So C again is defined over a finite extension of your field of definition, and again assume it is defined over the same Q bar of T. Okay, so the situation is like this. So it's very similar to what Laura discussed in our talk. So the picture is like that. You have a one-parameter family of plane mappings, okay, with a curve which is now moving with the parameter, so it becomes a surface, and you have plenty of preperiodic points living inside that. So it's a very similar to what Laura discussed in our talk, and so you have this mess of preperiodic points living inside this red surface. So the curve becomes now a surface, okay? And you want to get a contradiction out of this. Okay, so the first step of the proof is, so I said that when you specialize T to be a given algebraic numbers, we would like to apply the first part of the proof. So what we need is that for this algebraic number, there are infinitely many periodic points on the curve. And what could happen is that we may be unlucky, and that for these algebraic parameters, all these blue curves collide to a finite set. Okay, and we might be very unlucky, and this happens at every algebraic parameter. A priori, this could happen at countably many parameters, and we might be unlucky, and these countably many parameters could be the whole algebraic numbers. Okay, so we have to exclude this possibility. So there will be 3 lemmas, basically 2 lemmas. So lemma 1 is that this very unlikely situation that all blue curves collide at all algebraic parameters does not happen. Okay, so that's lemma 1. Outside finitely many exceptions, when you specialize the parameter to an algebraic parameter, you do get infinitely many points in this intersection. Okay, and to do this, so this is, maybe I should have said it earlier. So we already solved this dynamical Manin-Mumford problem for Henon maps with Charles a couple of years ago. So it's not polarized setting, but of course it's also an interesting dynamical setting. And we already had to face this argument, and we found a way of doing this. So first, assume that all these blue curves, they are not preperiodic points, but curves of periodic points. Now, assume that, well, you know what happens when 2 periodic points collide. What you have in the fiber of collision is a parabolic point. So a point of bigger multiplicity. So now, if infinitely many periodic points collide at this curve, you will get it's not true that you will get a point of infinite multiplicity, but at least the multiplicity of the point of the collision points grows with the iteration. And there's a theorem in smooth dynamics called the Shoup-Sullivan theorem, which says that this is not possible. Okay, so infinite collisions of periodic points are not possible due to a counting of multiplicity. Okay, so it's not, well, for people from one-dimensional rational dynamics, when you have a parabolic point and you iterate, the multiplicity does not change. The coefficient in terms of the second term changes, but not the multiplicity. That's the argument. It's also true in 2 dimensions, that's the Shoup-Sullivan theorem. Okay, so that's for collisions of periodic points. And now, so we know that now we have to go from periodic to preperiodic, and then there's another danger. It could be, the situation happens that infinitely many preperiodic points can collide at a point. Okay, and it only happens when you have a super attracting point whose multiplicity changes. So it's a phenomenon that had been studied by Keogh and Roder. And so these collisions are associated to changes of multiplicities for super attractive points. And so here we are talking about super attractive points in A2, so it can happen, okay? But it can only happen at finitely many points. So when I say that outside finitely many exceptions, you don't have this infinite collision. Okay, so now we are happy. We know that we can apply the first part of the proof for almost all algebraic points. Okay, the next thing, so let's do it. So for any point in, so S is the base, same notation, I think that is Laura's talk. S is the base of this family. And so now we know that for every algebraic point in S outside the finite set, we can apply the first part. In particular, by the Zhang theorem, we know that the point at infinity is preperiodic. So for every such t, so I pick a point, let me pick a point P, P sub t at infinity for my curve. And I know that for every algebraic t, we have a relation like that. But of course, everything depends on t. Okay, the pre-period, the period, and even then the points on the point on which it will fall depend on t. Okay, so lemma 2 is that all this does not depend on t. Okay, so maybe you have to exclude some other finite sets. So what is the time here? Okay, just on time. So lemma 2 is that P is preperiodic, and so how do you prove this? So you fix such an algebraic parameter which satisfies the previous lemma, so that we can apply the first part. So we know that this point P t0. So for the parameter t0. Okay, the point pt0 at infinity is periodic. You iterate so that it is fixed. Okay, and so it is now fixed. And this fixed point can also be continued as a fixed point. Let me denote by qt the continuation in pt, not as pt, not as a point of intersection between the curve and the infinity, but as a periodic point. So you have this qt and pt, and for the parameter t0, they collide. But they coincide, they coincide. Okay, and what we want to show is that they actually coincide in some neighborhood of t0. And then by analytic continuation, you will get they coincide all the time. And then it exactly means that this point P, viewed as a point of the bigger field, is a periodic point. Okay, now we claim that this is easier when the point is attracting. Okay, so now we are happy when this point qt naught is attracting. Why are we happy? The reason is that, so again, you have this point pt and you have q. So q is the continuation of the periodic point, s p is the continuation of the intersection. So if this point q is attracting at t naught, then in some neighborhood of t naught, it will continue to attract the point p. Okay, so now this point p for some neighborhood of t naught, it must converge to q. But also we know that this is preperiodic, so it can be preperiodic only to q. Okay, so we know, so we don't know that the preperiod does not depend on t, but at least we know what the limit point is. And also, if you think about it, in the basis of an attracting point, if you're sufficiently close to the attracting point itself, there's only one preperiodic point, which is the attracting point itself. Okay, so that's the proof for the attracting case. Okay, so when at t0 the point qt0 is attracting, then you're okay. And then again, we apply the same product formula argument. So either, so you look at all possible places, either the point is parabolic, or there is some place where it is attracting. So, and the argument I gave is valid over the complex numbers, but also over the p-adic numbers. Okay, so two cases, either there is a place where the point is attracting and then you are done, or it is always parabolic and then you need some other argument, which is somehow the same version. So a parabolic point in, so if it is parabolic, we work over the complex numbers, then you have a basin, you have an attracting petal, you also have a basin of a parabolic point, and we basically apply the same idea. Okay, and we need the classification by Gautier of families with a full bifurcation locus. Okay, so it's basically the same argument with a little twist because we are working with a parabolic. Okay, so now we are almost done. We know that this point is always, so it is preperiodic as the point of the bigger field. And so we can conclude the proof. We know that this point is preperiodic, and by assumption, our assumption is still valid, we know that it is not super attracting, pre-super attracting. Then you can always assume that this P is fixed. And the last step of the proof is to remember that, let me maybe go back to this. That would be the last sentence. In this situation, so we start with this preperiodic curve. We look at the point at infinity. We make it fixed by some finite iteration. And then the curve is itself fixed. The curve is not preperiodic anymore. So the curve, actually, what a corollary of proof is that the preperiod of the curve is the same as the preperiod of the point at infinity. Okay, so now let's come back to this last slide. So I replace by some iterate, and I know that for every algebraic T0, the curve C0 is fixed. It's not only preperiodic, but it is fixed now that I fix the point at infinity. So you have an equation like this for all algebraic numbers, but then just by density, by usual density, it is true all the time. And this being true all the time means exactly that the curve is periodic. That's it.